So z-scores are measures of position and are suitable if the data is symmetric in the sense it must have a bell-shaped distribution. If it doesn't, then z-scores aren't very useful. First, how do we compute a z-score? Suppose a data set has mean x bar and a standard deviation of s. Clearly, the data set has to be bell-shaped. In other words, a normal distribution. Let's say x is an observation or a data point. Then the z-score of x is simply given by this formula. X minus x bar divided by s. So x bar is the mean. S is the standard deviation, and x is the observation. So a z-score simply tells you a distance, or gives you the distance between the mean and the observation standardized by the standard deviation. I will use a bell curve to demonstrate this. Let's take that bell curve, and let's make some modifications here. And we know that's the mean, one standard deviation away from the mean, two standard deviations away from the mean, three standard deviations away from the mean on the right-hand side, one standard deviation away from the mean, two standard deviations away from the mean, three standard deviations away from the mean on the left-hand side. The percent there is 0.15%. Percent there is 0.15%. That's what we saw with the empirical rule. Now, I want to find the z-score corresponding to each of these data points that I see. X bar minus 3s, x bar minus 2s, and so forth. Before we get to that, I'm going to rewrite rewrite this expression, and I'll say, or we will say, that the observation corresponding to a z-score is given by this formula. So if I rewrite our formula to find the z-score, by multiplying s on both sides, I will have z times s equals x minus x bar. Add x bar to both sides, I'll have x bar plus z multiplied by s. So if we pay close attention, you will notice x bar plus z multiplied by s, and compare that to what we wrote here. So x bar plus s, I could write it as x bar plus 1 times s. So the z-score right there is 1. Similarly, x bar plus 2s, the z-score of that observation is 2. For that data point, the z-score is 3. On the other side, I could write x bar minus s as x bar the next data point as x bar plus negative 2 times s, the next one as x bar plus negative 3 times s. So on the other side, I have those z values to be -1, -2, and -3. So what does a z-score measure? If you notice, each of those points that we wrote in terms or in steps of the standard deviation. So the z-score simply measures the number of standard deviations of an observation, otherwise a data point, from the mean. So the sign indicates if it's to the right of the mean or if it's to the left of the mean. So the sign, well, a positive z-score would simply imply that the data point is to the right of the mean. A negative z-score would mean that the data point is to the left of the mean. Now one may ask, well, what if we had a 0 z-score? Well, if you look at x bar, I could rewrite x bar as x bar plus 0 times. So the mean of a sample has a 0 z-score. Now, as I mentioned, Z-scores are measures of position. In other words, they tell us where a particular observation lies relative to the mean. And oftentimes we can compare multiple samples using Z-scores, but the only condition here is that the samples have to have a bell curve. If we use a Z-score for inference, for samples that are not bell-shaped, then we're just lying to people. So the data must follow a bell-shaped distribution. And if it did, then we can use Z-scores to come up with inference. So men versus women. So the average 20 to 29-year-old man is 69.6 inches tall with a standard deviation of 3 inches, while the average 20 to 29-year-old woman is 64 inches tall with a standard deviation of 3.8 inches. Who is relatively taller, a 75-inch man or a 70-inch woman? So now you may just look at the raw numbers and come to a conclusion, oh, 75 is definitely bigger than 70, so it has to be the man. But that is not the question here. The key word here is relatively taller. Relative to your group, among all females, are you considered a tall person? Among all males, are you considered a tall person? So we want to look at the comparison in a relative sense. So we'll go with men first, then women. We have mean for men as 69.6 inches. Standard deviation is 3 inches. Women have mean as 64.1 inches. Standard deviation 3.8 inches. The observation here that's given to us is 75 inches for men, for a man. And here for a woman, we have 70 inches. All we have to do is to find the Z-score. So I'll put for male, it is X minus X bar over S, 75 minus 69.6 divided by 3, which would give us 5.4 over 3. And that is 1.8. So the Z-score for a 75-inch man is 1.8. So we could do the same here for females, X minus X bar over S. The observation is 70. The mean is 64.1. The standard deviation is 3.8. So we will have 5.9 divided by 3.8. That should be close to 1.7. Let me check. We could use a calculator, of course, to find that. 1.55. So now on the Z-score scale, relatively speaking, generally speaking, we would put males and females separately. because clearly, they are different groups. But the moment you convert them to z-scores, they sort of fall on the same scale, which is the z-score scale. So if I drew the z-score scale, that is our ranking scale, male is at 1.8, female is at 1.55, we can make a direct comparison and conclude, relatively speaking, the 75-inch man is going to be greater than the 70-inch woman. That is the purpose of a z-score, and that's why we call it or call z-scores as measures of position. So this is about Ryan Murphy. Apparently he's a swimmer and the nephew of the author. So two competitions are considered. One is the 100-meter backstroke. The other is the 200-meter backstroke. They are separate groups, but if I want to make a relative assessment, I need to bring them on the same scale. So how do I bring them on the same scale? By converting the raw observations to a z-score. So for the 100 meters, they have a mean of 48.62 seconds. The standard deviation is 0.98 seconds. The observation for Ryan there is, we'll call it X1, it's 45.3 seconds. In the 200-meter race, the average happens to be 99.32. The standard deviation is 0.98. Is it? No. Sorry. I have it backwards. The mean is 106.58 for Ryan. The standard deviation is 2.38 seconds. And Ryan's amount or time is 99.32 seconds. Now we can convert the observations to z-scores and put them on the z-score scale. So for the 100 meters, it's simply x1 minus x1 bar over s1. So x1 is 48.62 minus, 45.3 minus 48.62, which is the mean, divided by the standard deviation, 0.98. We get negative 3.387. In the 200 meters, we have 106.58 as the average. So 99.32 minus 106.58 divided by 2.38, which is the standard deviation. So we end up getting negative 3.05. If we put it in the z-score scale, I'll put it on the z-score scale. The moment we convert to z-scores, the observations become standardized. So for the 200 meters, it was at negative 3.05, and the 100 meters, it was at negative 3.387. So in which race is Ryan better? Relatively speaking, Z2 is bigger than Z1. So he's going to be better at the second race when compared to the first race. So for a student to get at least 1.5, in other words, 1.5 or higher. So if I compute the score for that Z score, then I'll know what that. So we know the formula to find the value of an observation, X, if a Z score is given, which is X bar plus Z multiplied by S. So X bar in this case is 200, Z is 1.5, the standard deviation is 26. So that is 200 plus 3 over 2 times 26. And if we simplify, we will get 200 plus 39, which would be 239. So for acceptance, the applicant must have a score of 239 or higher.